Here are two lines from our fraud job. The first filters 2 billion swipes to the last 30 days. The second groups those swipes by card and counts them. To look at, they're the same kind of thing. The filter takes about 30 seconds. The group takes 25 minutes. Same cluster, same data, 50 times the difference. Today, we find out why, because the answer is the most important thing to understand about Spark, and once you have it, most performance questions answer themselves. Two lines of code side by side with stopwatches beneath them, one reading 30 seconds and the other 25 minutes. Start with the fast one. Our data is sitting in 3,200 partitions spread across 100 executors, and each executor is looking at the partitions it happens to hold. Filtering to the last 30 days means asking for each row, is this date recent enough? And an executor holding partition 412 can answer that completely on its own. It does not need to know what is in partition 900 or what any other machine is doing. It reads its own rows, keeps some, discards the rest, and produces a smaller partition. Every executor does that at the same time, entirely independently, and nothing ever leaves the machine it started on. Many executors each filtering their own partition in place, no arrows between machines, labeled "every machine works alone." That is what Spark calls a narrow operation. One input partition produces one output partition, and no data crosses between machines. Filters are narrow. So is adding a computed column. So is anything you can decide row by row. Now the slow one, and here's where it gets interesting. We want, for each card, how many times it was swiped. Take one card, say card ending 4532. Where are its swipes? Everywhere. That card was used on Monday, on Thursday, at a supermarket, at a petrol station, online. Those transactions arrived at different times and landed in different files, which became different partitions on different machines. Nothing about how the data was written put one card's rows together. An active card used a few times a day might have its month of rows sitting in 50 different partitions on dozens of separate machines. But here's the stronger way to see it. Turn it around and look at one partition. It holds 128 megabytes of swipes from whenever they happen to arrive, which means fragments of millions of different cards, almost none of them complete. Every partition holds a little bit of nearly every answer. One highlighted card number with its transactions scattered as dots across many separate executor boxes, labeled one card, rows on dozens of machines. Now the problem is obvious. No single machine can count that card's transactions because no single machine has them all. Every executor holds a fragment of the answer and none holds the answer. So before you can count anything, the data has to be physically rearranged so that every row belonging to one card ends up in the same place. And that rearrangement is a shuffle. Scattered dots of the same color being gathered from many machines into one destination machine, labeled all rows for one card, one place. Pause the video and think about how you would actually do that, because the mechanism is worth working out yourself. You have 3,200 partitions on 100 machines. Every row needs to reach a specific destination based on its card number. No machine can see the whole picture. Here is how it works. First, every machine decides where each of its rows needs to go. It takes the card number, runs it through a hash function, and divides by the number of output partitions. That count is a setting, and Spark has a default it will use unless you say otherwise. We will use 200 here. Choosing that number badly is its own kind of trouble, and we'll come back to it. That gives a number from 0 to 199, and that is the destination partition for that row. The crucial property is that this calculation is identical everywhere. Every machine, working alone, sends card 4532 to exactly the same destination, because the same card number always hashes to the same number. Nobody has to coordinate. A card number entering a hash function and coming out as a destination number, with 3 separate machines all computing the same destination for the same card. Then, every machine sorts its rows into buckets, one per destination, and writes them to its local disk. Note that. Disk, not memory. This is the map side right, the first cost of a shuffle. Every row gets serialized, meaning converted into a compact stream of bytes, and written down. An executor sorting its rows into 200 labeled buckets and writing them to a local disk icon, labeled written out, not kept in memory. Now the other half. Each of the 200 destination partitions is assigned to some executor, and that executor now has to go and collect its share. Partition 17 has a fragment sitting on machine 1 and machine 2 and machine 3, and so on across all 100 of them. So it opens connections and fetches its piece from every single machine that has one. Every other executor is doing the same thing at the same time. 100 machines, all pulling from 100 machines across the network simultaneously. Then each fetched piece has to be deserialized, turned back from bytes into usable rows, and combined. Image. A dense web of arrows as every executor fetches fragments from every other executor at once, labeled every machine pulls from every machine. So, look at serializing every row, writing all of it to disk, sending all of it over the network, reading it back, deserializing it, and there is one more cost waiting at the end. If a destination partition turns out to be larger than the memory set aside to hold it, the receiving machine has to write part of it out to disk to keep going. That is called spilling. It is normal rather than an error, and it has an episode of its own later on. That is why the group took 25 minutes and the filter took 30 seconds. Not because grouping is a harder calculation, the counting itself is trivial. It's that the data had to physically move. Operations that need this are called wide operations. Grouping by a key, joining two data sets on a key, counting distinct values, sorting globally. Anything where the answer depends on rows that are not guaranteed to be sitting together. Image. Two labeled columns reading narrow, filter, add column, data stays put, and wide, reading group, join, sort, data moves. Now the part that makes the Spark interface suddenly readable. Look at any Spark job and you will see it divided into things called stages. People treat that word mysterious. It is not, and the definition is exactly one sentence. A stage is the run of work that can happen without moving data. A stage boundary is a shuffle. That is it. Spark takes your plan, walks through it, and every time it hits an operation that requires data to move, it draws a line. Everything before the line is one stage, everything after is the next. Image. A chain of operations with a vertical line drawn where data must move, labeled Stage 1 on the left, Shuffle on the line, Stage 2 on the right, which gives you a useful habit. Open your job, count the stages, subtract 1, and you know how many times your dataset was written to disk and dragged across the network. If a job you expected to be simple has 7 stages, you know what to go looking for. And this is also why the walls we mentioned last episode are walls. Spark cannot start the second stage until the first has completely finished, because the shuffle needs every machine's contribution before any destination is complete. One slow task at the end of the stage holds up everything behind it, and that becomes a whole episode later in the series. A stage bar where 199 tasks are complete and one is still running, with the next stage blocked behind it, labeled Everybody Waits for the Last One. So, the honest question, if shuffles are this expensive, can you avoid them? Sometimes. If one side of a join is small enough, Spark can send a copy of it to every machine instead, and then the join becomes narrow with no movement of the big cable at all. That trick is worth an episode on its own. You can also arrange your data on disk so that rows which belong together are already stored together, which is a later episode too. But often you cannot avoid it, and that is fine. Computing spend per card genuinely requires bringing each card's rows together. There is no clever way around it. The goal is never 0 shuffles. It is not shuffling more than the answer actually requires and not shuffling more data than the answer needs. A balance showing shuffles you need against shuffles you accidentally caused, headed "The goal is not 0." So here's the big picture. Narrow operations happen inside a partition, and each machine works alone. Wide operations need rows that live on other machines, so the data must be physically regrouped. That regrouping is a shuffle, and it means serializing, writing to local disk, fetching across the network from every machine to every machine, and deserializing again. It is by far the most expensive thing your job does. Stages are simply the pieces between shuffles, so counting stages counts how many times your data was moved. A summary strip reading narrow stays put, then wide must move, then moving is the cost, then stage boundary equals shuffle. Now, we have said twice that Spark rearranges your plan. It moved our filter before our join. It decides where to draw stage boundaries. It chooses how to perform a join. So who is doing all of this? Because it's not you, and it's not happening by accident. There is a piece of Spark whose entire job is to take what you wrote and turn it into something quite different. And next time, we are going to watch it work and read the plan it produces.